Hello, welcome to a video about the wave behaviour of particles. So we've looked at wave particle duality and we've looked at the particle nature of light, but now it's time to look at the wave behaviour of particles. Sorry if you can hear some doggy noises in the background, I'm just minding my friend's pup. So particles exhibit wave behaviour with a wavelength that depends on the momentum of the particle. The de Broglie wavelength can be determined using the formula wavelength equals Planck's constant divided by momentum, where h is obviously Planck's constant and p is the momentum of particles. The wave behaviour of particles can be demonstrated using a double slit experiment and the Davison-Germer experiment. In stage 2 physics, you need to be able to solve problems involving the use of this formula for electrons and other particles. You also need to be able to describe two-slit interference patterns produced by electrons in double-slit experiments. You'll need to be able to describe the Davison-Germer experiment in which the diffraction of electrons by the surface layers of a crystal lattice was observed, and you'll need to be able to compare the de Broglie wavelength of electrons with the wavelength required to produce the observations of the Davison-Germer experiment and two-slit interference experiments. So first we're going to have a look at the de Broglie wavelength. It looks like de Broglie, but it's a French name and I'm pretty sure it's pronounced de Broglie. So Louis de Broglie suggested that since light demonstrated particle properties, perhaps then matter also possessed wave-particle duality and demonstrated wave-like properties. And he quantified this theory by predicting that particle wavelength was equal to Planck's constant divided by momentum, which is equal to Planck's constant divided by the mass times velocity of the given particle. So given this wavelength and momentum relationship, if electrons in a Davison-Germer experiment were detected travelling with a velocity at 4.0 by 10 to the 6 metres per second, what is their wavelength if their mass is 9.11 by 10 to the negative 31 kilos, so the mass of an electron? Obviously we haven't gone through what the Davison-Germer experiment is yet in this video. I'll explain that in a moment, but we can still have a look at this example given what we already know about the wavelength of particles. So to do this, we know that the wavelength of a particle, in this case electrons, is going to be equal to Planck's constant divided by the momentum of the electrons. And we know that momentum is equal to mass times by velocity. So our rule for the wavelength of the electron is going to be the Planck's constant divided by the mass by velocity of the electron. We know that Planck's constant is 6.63 by 10 to the negative 34 joule seconds. We know that the velocity, or if we've been told the velocity of the electrons is 4.0 by 10 to the 6 meters per second, and we know that the mass of an electron is 9.11 by 10 to the negative 31 kilos, and you'll have this value on your formula sheet. So the wavelength is going to be equal to 6.63 by 10 to the negative 34 divided by the mass of an electron, which is 9.11 by 10 to the negative 31 kilos, and then the velocity is going to be 4.0 by 10 to the 6 meters per second. So if you then popped all of that into your calculator, you'd end up with an answer of 1.82 by 10 to the negative 10 meters, and this is equal to 0.1 0.18 nanometers. So the wavelength of an electron in this experiment, in this scenario, is equal to 1.82 by 10 to the negative 10 meters, or 0.18 nanometers. So now we're going to look at what is the Davison-Germer experiment. So Davison and Germer observed that a beam of electrons produced a diffraction pattern when reflected from the surface of a nickel crystal. I've got the experiment written out here, but I think it would be more beneficial for me to go to the next slide, which actually has the experiment diagram, but you can refer back to what I've written out here when you're doing your revision. So in our Davison-Germer experiment setup, we've got a circuit here that is connected to a plate which is going to fire a beam of electrons at a target. That electron beam is going to be low energy, and the target is going to be made up of a nickel crystal. The electrons are accelerated through a known voltage or a known potential difference, and therefore their speed can be determined. The reason that nickel is used in the target, so maybe you might want to write, just annotate nickel. The reason this is used is because the distance between atoms is 0.22 nanometers, which is comparable to the electron wavelength predicted by de Broglie's equation. So I'm going to say D equals, oh god, this is shocking. I need to get a new pen or a new, in fact I might just get an entire new iPad and Apple Pencil instead of plebbing around with this rubbish, but anyway, we'll have to make do for this video. So yeah, the distance between nickel atoms is equal to 0.22 nanometers, which is equivalent or in the same ballpark as the wavelength of an electron predicted by de Broglie's equation. The nickel target reflects the electrons at various angles, and this detector here is swung around an axis to intercept all the electrons that are being scattered, and then a sequence of maxima and minima intensities are detected. So you might have like a maxima here. Actually, I'm going to get a different colour. You might have a maxima here, and a maxima here, and a maxima here, and then like Young's experiment, you'd have minimas here, or a diffraction experiment, minimas here, here, and here. So like waves that are, or light waves that are being passed through a double slit, you end up with maxima and minimas. If these electrons are scattered from this nickel crystal target, and a detector is moved around an axis, then you'll get maxima and minima detection. So all the X-rays being scattered to certain points, and then no X-rays being scattered in between those points. The, I guess, theory behind this electron and nickel interaction is that electrons exhibit wave properties as they approach nickel atoms. So just like light is a wave, or it's a wave in a particle, but just as we think about light being a wave as it approaches like a mirror or something like that, or a reflective surface, X-rays approach the nickel surface as a wave. The nickel reflects these electron waves, and some electron waves reflect from adjacent nickel atoms, and they maintain a constant phase relationship. So this is where our path difference formula comes in. So path difference is equal to an integer number multiplied by the wavelength, or it's equal to d. So kind of like d being the distance between slits, in this situation, D is the distance between nickel atoms, and the path difference is equal to the distance between the atoms multiplied by sine theta, where theta is the angle of incidence. And if the path difference is equal to an integer number multiplied by the electron wavelength, then the electron waves will be in phase, even though they might be like one whole wavelength or two whole wavelengths or three whole wavelengths, etc., behind the given other, or like the next electron wave that it's interacting with. Where the phase relationship is constant and where it is a full integer out from the next wave, the constructive interference will occur there, and that's where you'll get an electron wave maxima. And then obviously where destructive interference is occurring, you're going to get minima occurring, so electron wave minima. So I've got a couple of examples here. If the angular position of the first order of maxima, so M1, detected in a Davison-Germer experiment is 50 degrees, what is the wavelength of the electrons? So to do this, we know that our theta is going to be 50 degrees. We're looking for our wavelength, and m is equal to 1. So we just use our d sine theta equals m lambda rule. And because we're looking for lambda, this will rearrange to lambda equals d sine theta over m. We know that m, as I just said, is equal to 1. Lambda is 50, so we'll just sub these values in. And as I actually just realised I haven't included it in this question, as I said before, d is equal to 0.22 by 10 to the negative 9 metres, which is 0.22 nanometres, and that's the distance between the nickel atoms. So if we were to sub all of this in, lambda is going to be equal to 0.22 by 10 to the negative 9, and then sine, and then 50, and then m is going to be equal to 1, so this is all just going to be over 1. If we then pop that into our calculator, our lambda, or our wavelength, is going to be equal to 1.69 by 10 to the negative 10 metres. So that is going to be our wavelength of the electrons. Next question, what is the predicted wavelength of electrons with an energy of, that should be 5.4 electron volts, if you wouldn't mind adjusting that on your notes. Apologies. So what is the predicted wavelength of these electrons? So ultimately for this, what we want to be able to do is use the wavelength equals Planck's constant divided by momentum equation, which is going to be equal to Planck's constant divided by the mass of an electron times by the velocity of an electron. To connect what we already know with what we want to know, we can look over here and see that the energy of the electrons is 5.4 electron volts. We can use the kinetic energy formula. Kinetic energy equals half by mv squared, because we're going to know the mass of the electron, because it's going to be given on our formula sheet. We're told the energy of the electron. We just need to convert electron volts into joules, and then that will let us find out what the velocity is if we rearrange the equation, and then we'll be able to sub that back into our wavelength equation, and ultimately determine what the wavelength of the electrons is, because we're going to be able to again get this value from our formula sheet, and then the Planck's constant is always a constant as well. If we want to convert 5.4 electron volts into joules, we just need to multiply 5.4 by 1.6 by 10 to the negative 19, and that will give us 8.64 by 10 to the 18 joules. So this is the value that we'll work with when we're subbing it into our kinetic energy equation. I'm going to rearrange this equation now. So if we're looking to make velocity the subject, rearranging this is going to become velocity is equal to the square root of 2 times kinetic energy divided by, sorry, I got a noisy pup, divided by the mass. So hopefully you can see I'm just multiplying both sides by 2. That will bring the 2, or to multiply the kinetic energy by 2, and it will cancel out with the half on the right hand side of the equation. Then I'm dividing both sides by the mass, and then I'm taking the square root of both sides of the equation. Now we've got the kinetic energy, which is this value here. We know that the mass is 9.11 by 10 to the negative 31. So we're going to be able to work out what the velocity is. So I'll just quickly sub those values in now. So 2 by 8.64 by 10 to the 18 square root, and then 9.11 by 10 to the negative 34. Therefore, our velocity is going to be equal to 4.36 multiplied by 10 to the 6 meters per second. If we then want to work out our wavelength, so back to this equation here, we've got all the information that we need to fill in Planck's constant divided by mass times velocity. Planck's constant is going to be 6.63 by 10 to the negative 34. Mass is going to be 9.11 by 10 to the negative 31. I've just realised I've put 34 over here. That's just meant to be 31. Sorry. May as well just rub it out and make it nice and neat. Oh, I can't rub out when it's zoomed in. I'll just cross it all out and then write negative 31, negative 31. Alright. And then our velocity is 4.36 by 10 to the 6 meters per second. If you pop all of this into your calculator, you're going to end up with a wavelength of 1.67 by 10 to the negative 10 meters. So the predicted wavelength of electrons with an energy of 5.4 electron volts is going to be 1.67 by 10 to the negative 10 meters. In reality, when this experiment was conducted, the predicted value is very similar to the measured value, and this supported the wave particle duality of electrons, or the idea of electrons having a wave particle duality. So just like Young investigated light with a double slit experiment, electrons have also been investigated using a double slit experiment. Single electrons are passed through slits and then end up being detected by a detector of some sort. Electrons, like light, produce a two-slit interference pattern despite their particle nature, or the particle nature that we assume or presumed that they, or originally presumed that they only had. And this obviously contrasts with the expectation that you'd have that would just be having two fringes of electrons that would just be parallel to the slit. So if particles are passing through two slits, they can only pass through those two possible slits. So you'd expect that the detector would just detect particles that have come directly through those slits. But that didn't happen. A two-slit interference pattern, like light, was produced. So this suggests perhaps that each electron passes through both slits simultaneously, then interferes with itself, and produces a two-slit interference pattern. So it's hard to think about this if you're only thinking of electrons as particles, but if you were to allow a bit of flexibility in your mind and think, well, what if we just consider electrons as waves? Then it is possible that an electron, if it's a wave, it's possible that it could pass through the two slits simultaneously, therefore interfere with itself and produce this two-slit interference pattern. So I think the probably the most challenging aspect of this is to release the notion that electrons are only particles, and as soon as you can think about electrons in terms of waves, then it becomes a little bit easier to, I guess, comprehend or retain this information, so it's not contradicting the information that you already have in your head. So you just kind of have to make that adjustment in order to, I guess, let this one sink in. So just like when you adjust the intensity of light in a diffraction experiment, the fringes are like more or less obvious. If it's less intense, if the light is less intense, then the fringes are less obvious. An electron diffraction pattern can build up over time. So in the first image, it just kind of looks like nothing's too defined. But then as the electron diffraction pattern builds up over time, the fringes become more and more defined until they're quite obvious in the last picture.